Welcome to Tvaritam.AI. In this video, we will understand gradient boosting. Now, in our video about random forest, we discussed bagging as an ensemble learning method. Just for a quick recap, bagging trains multiple models in parallel, gives equal importance to each model and averages their outputs. This helps in reducing the variance of the model. When it comes to boosting, which is another widely used ensemble technique, the approach is a little bit different. Here models are trained sequentially and each model focuses on correcting the error made by the previous one. Because of this iterative improvement, boosting can effectively reduce both bias and variance, often leading to very strong performance on both training and test data. Now let's talk specifically about gradient boosting. Gradient boosting is a boosting technique where models are built sequentially to minimize the overall error of the system using gradients. Here the intuition is that we start with a simple prediction, this could even be a constant value. Next we compute the residuals, which are simply the errors between the actual values and our predictions. Then we train a new decision tree to predict these residuals. The key idea is that we update our original prediction using the new model. The update rule looks like this, where the updated prediction is equal to the previous prediction and we add the product of learning rate and the new prediction. The new prediction h of x that you see is actually the residuals that are being predicted by the new tree and not the actual target variable. By repeating this process step by step, the model gradually improves and moves closer to the actual values. And in the next part, we will understand this entire process with a simple example, and we will also understand the update rule step by step. So what you see on your screen is a small data set with 4 variables: size, bedrooms, age and price, where price would be our target variable. Now first we train a simple model that computes mean as the predicted value. So it is a baseline model and every sample gets the same prediction, 30.4. The residuals here are the difference between the prediction and the actual values, and in this example for our very first model they are considerably large, ranging from -12.4 to 16.6, and this is our model F0. Now we will train small trees moving forward and each tree will learn to predict the residuals from the prior step. Hence the new prediction should be equal to old prediction, and we will add the learning rate multiplied by the tree output, and we will keep the learning rate eta as 0.5 for this particular example. Now when we create our first tree that is based on the size of the room, we create a split at 1500. So left leaf size is less than 1500, right leaf size is greater than equal to 1500, and we calculate the residuals. So instead of calculating the actual values, that is 30.4 here, that was the value from previous tree, we predict these residuals -12.4, -6.4, and when we create a split, these are the resulting residuals. -5.6 are the ones that we get from the left leaf, plus 11.45 are the ones that we get from the right leaf. Now we multiply these predicted residuals to our learning rate eta, that is 0.5, so all of the values get halved. And our new prediction F1 is equal to F0, that is 30.4, and we add this residuals multiplied by the learning rate. So when we add these values to the values predicted by our previous model, we get the new values as F1. And now the next tree that we will create will try to reduce the residuals left behind by the F1 tree. Say in the next example, the second tree predicts the value by predicting the residuals left behind the first tree. So here we are using bedrooms greater than equal to 4. So if they are less than 4, we calculate the residuals. If they are greater than 4, we calculate another. So this is also a very small tree that we are creating with only one root node and 2 leaf nodes. So again we multiply the residuals by the learning rate. F2 now is equal to the predictions made by F1 plus the learning rate multiplied by the residuals predicted by the second tree. So these are the updated values that our model is predicting, and then we have the new residuals R2. Now we'll create another tree F3 which will try to fix the residuals R2, give us the output H3. I think we missed this. Yes, gives us the output H3. And in this case, we again multiply by 0.5. We add the value that we get after multiplication to the prediction of F2 and we give the value for F3. Now F3, our third function, is trying to reduce the errors given by the second tree. And after making these 3 trees, these are the final predictions that we have: 23.7, 36.4, 40.3, and these are the final residuals for this example. Now left leaf is based on age, right leaf is based on age greater than 15, left on age less than 15. So we have used all 3 variables and created 3 very small trees, and each tree is trying to reduce the error left behind by the previous tree. Now when this all happens, we can see that after every tree that we are computing, the error is going significantly down. And here after tree 1, the mean squared error goes less than 40, then it goes less than 30, and after the third tree it is very close to the minimum range that we can get. So we start with a baseline model which is just predicting the mean of the target and giving us large residuals, and tree 1 learns a single split. Tree 2 fits the leftover residuals R1, and T3 then targets to fit R2. In real world, we will create many more trees and we will have a lower learning rate, 0.1, even 0.01, 0.3, similar in this range depending on your problem type. And we will create more trees. More trees will give us more smoother and better convergence, and less trees are giving less smooth convergence, as you can see. So if you have a very big data set, here we only had 10 rows of data with 3 features. But when we have a large data set, we create multiple trees, and multiple trees can reduce the error left behind by the previous trees, which gives us a very strong test accuracy here. Now we will move forward with the hyperparameters in the gradient. Moving forward with the hyperparameters in gradient boosting, we have maximum number of trees. We have learning control hyperparameters like learning rate and early stopping. We have tree complexity hyperparameters for overfitting control like maximum depth, minimum samples per leaf, and maximum leaf nodes. And we have feature selection hyperparameter for maximum features. So starting with maximum iterations or trees, it controls the number of trees that are added sequentially. More trees generally provide with better learning capacity, but also poses a higher risk of overfitting and longer training time. So typical values are between 100 to 1000, but usually we should keep it between 100 to 500 for moderate problems. For maximum features, number of features considered at each split can be set as a threshold. So it adds randomness similar to random forest, and lower values can provide higher bias and lower variance. Typical values for classification is similar, like square root of the number of features, and for regression we can go with the number of values divided by 3. Now for learning control, we have the learning rate that shrinks contribution of each new tree. The core idea behind boosting, as we have discussed in the example where it was 0.5, but in real world it ranges between 0.01 to 0.1. Lower learning rate leads to more robust trees, but it will require more tree to reach to the minimum point of error. Rule of thumb, we can start with a lower learning rate and then we can gradually change depending on the validation accuracy. Early stopping stops training when validation performance stops improving. It prevents overfitting from too many trees. So we can give a patience of 10 to 50 iterations where if the validation loss does not improve, we can stop the training process. Tree-based hyperparameters are there to avoid overfitting, as gradient boosting method is more prone to overfitting when compared to a random forest model. So we should be careful with hyperparameters tuning, as it requires much more careful tuning as compared to bagging methods like random forest. Now maximum depth controls complexity of individual trees. Gradient boosting typically uses shallow trees or weak learners, and typical values can be kept between 3 to 8. Minimum leaf samples is the minimum samples required in a leaf node. It prevents very small and noisy splits, and we can keep 1 to 10 for small dataset and 10 to 100 for larger dataset. Maximum leaf nodes limits the number of terminal nodes in a tree. It controls the tree complexity directly, and it is useful for controlling overfitting, especially in boosting, and typical values can be kept between 10 to even 100 plus. This was about gradient boosting. Thank you.